Good morning. All right, so we are going to pick up where we left off in section 4.5, so that's example 9. Before we do that, though, I've got a few announcements and reminders about things. Number one, I did move the homework that was supposed to be due tonight, the 4.5 and 4.6 stuff. We're obviously not going to finish up 4.6 today, so I'm going to move that to the end of this week. That will also be when the test for chapter 4 is due. So just make sure that you're working on that, throughout the week so that you don't have all of that coming due on Friday night and, stressing out trying to get all of that done. Okay. But I am going to make that due on Friday night. The test will be posted Wednesday night at midnight, and that'll be due on Friday at midnight, as always, right? So just make sure that you set aside some time Thursday or Friday to take the chapter 4 test. The plan right now is to finish up 4.5, maybe get into 4.6 today, and then whatever we don't finish, we'll finish up on Wednesday. That'll leave us Thursday as a review day. So we will go through the practice test, which is posted now. So I just wanted to let you know that is up there if you want to start looking at it. But we will review that on Thursday. And like I said, the test itself will be due on Friday at midnight. Okay, so that's basically all of the chapter 4 stuff. Once we get through this week, we only really have one more week of class time remaining because I had set aside that entire first week of May as exam time. What I might end up doing is still allowing people, if they want to schedule their exams those first couple of days of the week, that's perfectly fine with me. But I'll probably also have some class meetings those first 2 days of that week, just for review time. Okay, so next week we'll do chapter 10. We'll get through as much of it as we can, right? So if I don't get through all of it, it's not a huge deal. And I'll just have to adjust the types of problems that I put on the final exam for that, depending on how much we get through. But then I do want to have some review time. And so I will take a couple of days that first week of May to review. But again, since I'd already promised you, Monday through Friday, you can choose an exam time. If you want to schedule it without any review, that's perfectly fine with me. If you want those review days, then you can just schedule yours later in the week. I will be sending out a survey for you to sign up for an exam. So unlike all of your other tests, where it's just, okay, it's open for 2 days, choose a time to go in and take it. I do want you to kind of set aside a time so that I know when everybody's going to be in there, and so that if there are any issues or anything, I can make sure I'm available to resolve them. Okay, so that's the main reason I have you actually schedule a 2-hour period for your final exam. All right, but again, it'll be one of those 5 days, first week of May. I'll send out that survey maybe later today, but definitely this week sometime, so that you can actually sign up for a time and choose when you want to do it. And again, I give you those 5 days to do it just because I know there's other exams and things, and I don't want stressing out about it. You've got to take it on a specific day. I'd rather you have a few days to choose from. Okay. All right. So I think that's all of my announcements. I know that was a lot. Okay. So are there any questions, comments, or concerns about anything I just said? Okay. It will still be a test on chapter 10, right? Because I had promised you 5 tests. I want to make sure I stick to that. The test number 5, though, will not be in Respondus. It will be open note, open book. So like I said, we'll get through as much of the chapter 10 material as we can next week. I'll post that test. It'll still be 2 days, but you'll have all 2 days to kind of work on it at your leisure whenever you want to. Use your notes, use your book. And you'll just submit that by Friday of next week at midnight. So just know that, this week you've got the one in Respondus on chapter 4, and then the chapter 10 material that we cover next week, that'll be open note, open book. It'll still be due on Friday at midnight, but you'll have, anytime you want to work on that is fine. Okay. You're actually choosing a time when you do that survey, right? So the survey will basically be choose a day and then choose a time, and it'll be a 2-hour window starting at 8 a.m., ending at 10 p.m. So that way I try to prevent people from taking it overnight, again, so that I can make sure I'm available if there are any issues for the final exam. So that's why it'll be like an 8 to 10 a.m., a 10 to noon, noon to 2, that kind of thing, all the way up until 10 p.m. at night. Okay, so just try to think of a 2-hour window, one of those 5 days that first week of May, between 8 a.m. and 10 p.m. that you can sit down and take that. Okay, but I'll send out that survey for you to actually select a time, not just tell me, what your preference is. Okay, it'll actually be choosing a time. All right. Any other questions there? All right. So again, if you think of anything, feel free to email me. Obviously, we have class the rest of the week too. So just, if you need to stop me at the beginning of class to ask a question, please do that, because I know there's a lot of stuff coming up and just a little bit of time left to do it. Okay. All right. So let's take a look here at example 9. We want to solve this equation. Okay. Now, if you remember, we started looking at exponential equations and logarithmic equations last week. The first thing we're always going to want to do if we're trying to solve a logarithmic equation like this one is we want to get the logarithm by itself first. Okay, so if I wanted to get this logarithm by itself, what would I need to do first with this equation? Good, we need to move the 4, right? So I'm going to subtract 4 from both sides here. Give me 1 second, my pen's not writing. There we go. All right, so we're going to subtract 4 from both sides of this equation. That's going to leave us with 3 log 2x equals, and then 16 minus 4 should give us a 12 over there. So again, trying to get the log by itself now, what would be our next step? Good, now we can divide by the 3, right? So I'm going to get rid of this 3 in front of the log. Divide both sides by 3. That'll give us the log of 2x equals 4. All right, now once we get that logarithm by itself, at that point, we're going to want to rewrite this thing in exponential form. So if I were to take this logarithm and write it in exponential form, what would that look like? Good, right? So we know this is a common log, which means its base is an understood 10. So then when we rewrite this in exponential form, it's going to be 10 to the 4th power is equal to 2x, which is inside here now. So we have 10 to the 4th equals 2x. Any questions on that step? All right, so now we just need to get x by itself. Let's go ahead and simplify first. What's 10 to the 4th power going to be? Good, 10,000, right? A 1 with 4 zeros. And so then we can do what to get x by itself? Good, just divide by 2. And that's going to give us 5,000 equals x, and that is our solution now. So again, if you have a single logarithm in an equation like that, first thing you want to do, isolate the logarithm, get it by itself, then we can rewrite it in exponential form, and once we rewrite it in exponential form, you should be able to just get the x by itself at that point. Any questions on that one now? All right. So let's take a look at this one now. So this time we've got an equation that has 2 logarithms in it. We got log of x plus 2 plus the log of x minus 1 equals 1. And we're asked to solve this algebraically and graphically. We'll do it algebraically first, and then we use the graph to kind of check ourselves. Now, if we have a logarithmic equation with multiple logarithms, the first thing we want to try to do is see if we can combine them into a single logarithm. So what could I do in this case if I wanted to combine these logarithms? Yeah, we're going to multiply, right? Because remember, addition of two logarithms, as long as they have the same base, we can multiply what's inside. So I'm going to rewrite this now as the log of x plus 2 times x minus 1, and that's going to be equal to 1 now. All right, now, once we've got it as a single logarithm, what can we do at that point? Okay, good. We can go ahead and FOIL that out if we want to. So now we've got the log of, we FOIL this now, x times x is going to give us x squared. Our outer terms, we're going to have a minus x, inner terms plus 2x, so that's going to give us a plus x overall. And then 2 times negative 1 is going to give us a negative 2. Any questions about how I got that? All right, so now that I've FOILed that, what can we do next? Good. Now we can convert it into exponential form, right? Because like I said, once you get a single logarithm by itself like this, we can rewrite it in exponential form to try to solve for x. Our base, again, is 10 because it's a common logarithm. So we're going to do 10 to the first power is equal to everything inside here now. So 10 to the first equals x squared plus x minus 2. All right, now what can we do to try to solve for x? Good, right? We need to set this equal to 0, right? Because we have a quadratic. So Destry, does it matter which order you did the last two steps? No, right? You could have rewritten it in exponential form first and then used your FOIL to multiply the x plus 2 times x minus 1. You're going to get the same thing either way, right? So yeah, so whether you simplify what's inside and then go to exponential form or go to exponential form and then simplify, it doesn't matter. Okay, that's a good question. All right, good. We're going to subtract 10 now, right? Because we want to set this equal to 0 so we can solve this quadratic. Now we're going to have 0 equals x squared plus x, and that's going to be a minus 12. All right, now what can we do from there? Good. Now we can factor, right? So what are the factors going to be for this trinomial over here? Good. So we need an x plus 4 and an x minus 3, right? Because our factors of 12, it's either 6 and 2, 4 and 3, or 12 and 1. In this case, though, we need a 1x in the middle. That tells us it needs to be the 4 and the 3. Because it's a positive x, we need a positive 4 and negative 3. That'll also give us the negative 12 down at the end. All right, now that we have our factors, what can we do? Good. Set each factor equal to 0. So we're going to have x plus 4 equals 0 and x minus 3 equals 0. And so that's going to give us what two solutions then? Good. X equals negative 4 and x equals positive 3. Now, we mentioned this last week, okay, but any time that we combine logarithms like this, what do we need to do now that we have our solutions? We got to check them. Good. We got to plug them back in, make sure they actually work. Because remember, we can't have any negatives inside of a logarithm. So if when I plug either one of these values in, it gives me a negative inside of a logarithm, then I know it can't work. So let's start with a -4 here. Okay. Now, again, don't assume that just because it's a negative value, it's not going to work. It could, right? But I'm going to plug it in here. I'm going to say -4 plus 2 plus the log of -4 minus 1. And I want to know, is that equal to 1, right? Now, when I simplify what's inside of my logarithms this time, what's -4 plus 2 going to give us? -2. So automatically, what does that tell us then? Okay, it's not a real number, right? We're not going to get a solution from this. And so this -4 down here does not actually work. Okay, now I just cross these out most of the time just to make sure it's clear. Oh yeah, the -4 doesn't work. It's not a real solution. This is what's called extraneous. Okay, so if you ever hear that term, notice that the root word there is extra. So it's basically an extra solution that when we do this algebraically, we get, but it doesn't actually work, right? So we call that an extraneous solution. And you would see in this case, the other logarithm also gives us a negative, right? So neither one of those is going to work. And so that doesn't work, okay? So, okay, Matthew, that's correct, right? And that's why this solution shows up, is because once I multiply, the negative times negative actually gives us a positive, right? So it looks like it could work. The problem is the original equation was a log of x plus 2 plus a log of x minus 1. And when I put that -4 into either one of those logs don't work by themselves, right? Okay, so you have to go back to the original equation when you substitute in. That's right. So it's the combining here that makes it look like that solution should work. But if you go back to the original equation, we have a negative inside the logarithms. So that's why it doesn't actually work. Now let's check 3, right, just to make sure it works, right? Because it could be that both of these are extraneous. But if I plug in the 3 this time, I have log of 3 plus 2 plus the log of 3 minus 1 equals 1. Well, what's the log of 3 plus 2? Or what is 3 plus 2? It's going to give us 5, and then 3 minus 1 would give us 2. In this case, both of those are positive, right? And you can see once we multiply, it's going to give us a 10, and that's why this one checks out. Okay, but as long as we get positive values inside both, then we know that's a good solution. So this is our only solution this time. So again, you don't really have to finish it out and check all the way because as long as you did all your work correctly for the other piece, it's going to work out and give you the one that we want on the other side. It's just a matter of, do we end up with any negatives inside? That's really what we're checking for. Any questions on the algebraic way of solving that now? All right, so that also asks us to look at it graphically, right? So what I'm going to do is I'm going to graph the left-hand side as one equation, I'm going to graph the right-hand side as another, and then we're going to look for any points of intersection that we might have here. All right, so let me put that back. There we go. All right, so our left-hand side this time was log of x plus 2 plus the log of x minus 1. And then our other side was just a 1, right? So we're just trying to see, and I have to put y equals here, so y equals that. We're basically just saying now, where do these two equations over or intersect each other, right? That's what we're trying to find. Notice here, the only place that they intersect is at this point right here. And that's that x equals 3 that we got as our solution. So by looking at the graph now, we can see they don't intersect at -4. That's why -4 is actually an extraneous solution that we get algebraically that doesn't actually show up graphically now. This is a good way to kind of check yourself to make sure you found all of your extraneous solutions. Because in this case, if you got -4 and +3 and you look at the graph, you notice it doesn't actually intersect at -4. That solution's not actually going to work here. Okay. Any questions there now? All right. So let's take a look at this one now. So we've got x squared equals 2 natural log of x plus 2. All right, so let's see about doing this one algebraically. What do you think our first step would need to be if we were going to solve this? All right, good. So we want to isolate the logarithm first, right? So I'm going to divide both sides by the 2 out front. That's going to give us x squared over 2, or 1/2 x squared if you want to write it that way, equals the natural log of x plus 2. Okay? Now that we've got the logarithm by itself, what would our next step be? Okay, good. Go to exponential form. What's our base this time? E, right? So natural log, remember, has an understood base of E. So when I rewrite this in exponential form, it's going to be E to this power is equal to everything inside that logarithm. So we end up with E to the x squared over 2 equals x plus 2. Okay. What do you think you would do next? Okay, so remember the base of the natural log is an understood E, right? So common log has a base of 10, natural log has a base of E. So it's one of those things that we don't write when we write the natural log, but it's understood, so we can put it in there, so then we can rewrite it in exponential form. Okay. All right, so any ideas on what we might could do from here now if I'm trying to solve for x? All right, so multiplying by 2, the problem there, right, we can't do anything with the 2 that's up in the exponent, right? Because it's x squared over 2 all in the exponent together. So multiplying by 2 is not going to do anything. Subtracting 2, right, you could try that, but that's going to give us an x on the right, but we still have that x squared up in the exponent on the left, right? So think about it this way. Normally, if we had an x in the exponent, what would you want to do to both sides to get that x out of the exponent? You'd want to take a log of both sides, right? And in this case, you'd want to take a natural log since the base is e. But if I do that, so that I can get that x out of the exponent, what's going to happen? Okay, the natural log of e turns into 1, so this becomes x squared over 2 equals natural log of x plus 2. And where are we? Yeah, back to the beginning, right? Because if I multiply by the 2, now I'm back to where we started. Okay, so I end up in this loop, right, where I'm like, okay, I need to change this to exponential form to get rid of the logarithm, but then I need a logarithm to get rid of the exponent, right? And I can't actually get x by itself. If that happens, algebraically, we don't have a way to solve this, okay? And so the only way we can solve this one now is graphically. Okay, so I just wanted to show you though, right? If you were to try to do this algebraically, the reason we can't is because, changing it to exponential form gives us an x in the exponent. Trying to get that x out of the exponent gives us a logarithm back, and we just end up in a vicious cycle, right? So the only thing we can do here is to graph both sides of this equation and then look for points of intersection. Okay, so that's how we're going to do this one now. So I'm going to go back to Desmos. And so our left-hand side this time was just x squared, so we'll graph that. Other side was 2 natural log of x plus 2. So again, if we're using graphing, we're looking for points of intersection. Notice this time there are actually 2 points of intersection for these 2 graphs. So we're going to have one right here, and we'll have another one right up here. We're only looking at the x values because our equation was in terms of x. So our 2 solutions this time are going to be x equals negative 0.712 and x equals 1.601. Again, that's the only way we're going to be able to find our solutions to this equation, okay, because trying to do this algebraically, we just end up in a loop. Right? So we have to graph it, find points of intersection that way. Now, notice this time, we got a solution that is negative. That's perfectly fine, because if I substitute that back in, I'm adding 2 to that negative value. So inside the logarithm, I still actually have a positive value. That's what I was saying before. Don't just assume that all negative values don't work, okay, because depending on your equation, whatever you're doing inside the logarithm, you could end up with a positive once you actually substitute it in. Okay, so that's what we actually have to plug it in to test those solutions when we have those extraneous ones. Okay. Any questions on that one now? All right. So there it is, right? If you want your solutions, just x equals negative 0.712 and x equals 1.601. Again, in WebAssign, right, it would ask you for a comma separated list, so you would just write both of those with a comma between them. Okay. All right, we're gonna skip that one. I want to do this one. Okay, so a sum of $5,000 invested at an interest rate of 5% per year. We're going to find the time required for that money to double if the interest is compounded according to the following methods. Okay, so we're going to do this, and then we're going to do it continuously. All right, so first off, if we're going to do this semi-annually, what formula would we want to use this time? All right, good. We're going to use that compound interest formula. Make sure we're using the first one, right, because we actually have an n value this time. So that one was a of t equals p times 1 plus r over n to the nt. Now, let's start substituting what we know in this case, right? So do we know, well, tell me what we do know. Okay, so we know the p value is 5,000, right? Because that's how much we're investing. So that's our p, so we can put that in there. So that's 5,000. 1 is definitely 1, so I can do 1 plus. Right, what else? Oh, yeah, we know our rate, and we have to change that now to a decimal, so that's going to be 0.05. So 0.05 is our R value. we know anything else? The n value is going to be 2, right? So semi-annually means twice per year, and so our n value here is going to be 2. So n value in the exponent's also going to be a 2. Do we know anything else? Okay, so it doesn't really give us any other numbers, right? What are we trying to solve for? We're trying to solve for time, right? So we want to know what t is equal to. So I'm going to go ahead and put t in here because I know that's what I'm looking for. So the only thing I'm missing that's going to keep us from being able to solve for t now is the a of t value. Is there anything at all in this problem that tells us what a of t is going to be? Good, right? We want our money to double. Since we're starting with $5,000, if we want to double our money, that means we want to end up with $10,000 overall. So I'm going to set this equal to $10,000 this time. So just make sure you're reading through the problem, right? Because even though that 10,000 is not written as a number, it does tell us we want to double our money. We're starting with 5,000. That means we want to end up with 10,000. Now we've got everything we need to solve. If I want to get t by itself, what would I need to do first here? All right, good. Let's divide by the 5,000 on both sides. Do that. That's going to give us 2 equals. And then in here, I'm going to go ahead and simplify what's in the parentheses. So I'm going to do 1 plus 0.05 divided by 2. That's going to give us 1.025 to the 2t. Okay. Now what can we do? Good. Now we can take a log on both sides so we can get the t out of the exponent. So natural log works. So we'll do natural log of 2, natural log of 1.025 to the 2t. All right. What can we do from there? Good. Bring the exponent to the front. So I'm going to have natural log of 2 equals 2t natural log 1.025. And so now if we want to get t by itself, what can we do? Okay, good. We can divide by 2. Is there anything else we can divide by? Yeah, then well, not the natural log of 2, right? Because the natural log of 2 is already on the other side. So we'd actually want to divide by natural log of the 1.025, right? So I'm going to do both of those in the same step here. So we can just divide both sides by this now. Because that way I cancel out the 2, I cancel out the natural log of 1.025. That gives us our t value. And now we can just put this into the calculator to get an approximation for what that time is going to be. Make sure in this case that your entire denominator is grouped together, right? Because that 2 natural log of 1.025 needs to be multiplied before dividing. So if we do all of that now, what should that give us for our time? Okay, good. So 14, we round that off. And so that's going to be 14 what? And I'll go a couple of decimal places here. So 14.04 is what I got to 2 decimal places. Good. And our time is always going to be measured in years here. So this is telling us now that if we want to double our money at an interest rate of 5% per year, it would take 14.04 years if we compound semi-annually. So same formula we looked at before, okay, but now we have ways to solve for other variables, especially in this case, the time, right, because that time is in the exponent. Any questions about any of the steps for that one? All right, now the other piece of this was continuously. So what are we going to have to use if we want to do this continuously now? Yeah, that's the PERT formula, right? So this is going to be A of t equals P times E to the RT. Now, everything else is going to stay the same, right? So we know the R value, we know the P value, the A of t is still 10,000. So we're still going to plug all that stuff in. We're still solving for t. So this is just 10,000 equals 5,000 e to the 0.05 t. All right, so again, if I'm trying to solve for t, what's our first step going to be? Good, divide by that 5,000 again. 10,000 divided by 5,000 should give us 2 equals e to the 0.05 t. Right, now we can do what? Good, take your natural log. And in this case, you definitely want to use natural log because there's a base of e on the other side. We'll do natural log of 2 equals natural log of e to the 0.05 t. So now if we simplify the right-hand side, what's that going to give us? Good. Remember, natural log of e to some power is just going to give us whatever's in the exponent. So we're going to have natural log of 2 equals 0.05 t. All right. And then our last step then to get t by itself is to do what? Good. Just divide by that decimal. Divide both sides by 0.05. And so again, keep 2 decimal places here. How many years would it take then if we were to compound continuously? Good, 13.86. So notice here, right, it is slightly shorter, right, to double our money if we're compounding continuously compared to semi-annually. But in both cases, it's going to take almost 14 years, right, to be able to double that money at 5%. Any questions on that one now? Okay, so remember, natural log of e to this power, let me actually, I'm going to add a new slide in just to simplify that part. So I don't have to erase any of this. So we had natural log e to the 0.05 t. Technically, right, our steps would be to move the 0.05 t to the front, right, because we can move that out of the exponent. So we get 0.05 t natural log of e. But now, if I look at this natural log of e, remember the base of the natural log is e. So if I take the natural log of e, this just becomes 1. And so then we're really left with 0.05 t times 1 which is just 0.05 t. So the shortcut is just to say, well, if I've got natural log of e to some power, it's really just going to be equal to whatever's in the exponent, because that natural log of e just becomes a 1 anyway. Does that make sense? Oh, the natural log of 2. On the other side, I'm just putting that in the calculator at that point, right? So I'm just taking natural log of 2 and dividing by 0.05, just like we did on the other one, right? And that should give us that decimal. Any other questions there? All right, so that's all we've got for that section. All right, so we're going to go ahead and start looking at 4.6. Hopefully we can get through at least an example or two there. All right, so modeling with exponential functions. And so what we're going to look at now is, with some real world problems, how can we write exponential functions as models of those situations and then use those models to help us solve those problems? All right, so the first type of problem we're going to look at is what's called doubling time. Okay, so this is an exponential growth type of problem, okay, where we know that something doubles ever so often. So if the initial size of a population is n sub 0, so whenever you see that subscript of 0, that means initial. So this is our initial population. And the doubling time is a, so we're going to use a as our doubling time. The size of the population n of t at time t is this formula here. Okay, so again, we start with n sub 0, that's our initial. We're going to multiply by 2, so since we're doubling, we're going to use a base of 2. T is still time, and then a is our doubling time. Now, just make sure in this case that a and t need to be measured in the same units. Okay, so if t is in years, then a needs to be in years. If a is in minutes, then t needs to be in minutes. Okay, so just make sure they have the same units. And in some cases, you might have to do some conversions, right? If one's in hours and one's in minutes, we might have to convert to make sure they're in the same units. It's always initial times 2 to the t divided by a, where t is your time, a is your doubling time. Any questions on that formula right now? All right, so let's take a look at an example. So under ideal conditions, a certain bacteria population doubles, that should be every 3 hours. Initially, there are 1,000 bacteria in the colony. So we want to find a model for the bacteria population after t hours. So remember our formula here. As soon as I see the word doubles, that tells me I'm using my doubling time formula. So it's going to be n sub 0 for initial times 2 to the t divided by a. All right, so do we know the initial population this time? It's 1,000. Good. So initially there are 1,000, so that gives us our n sub 0. Do we know the a value? That's 3, right? So that's our doubling time. So that's 3. And notice here, we want our formula to be in terms of t, so we don't need a t value, right? We're just writing the model here. So this is going to be n of t is equal to 1,000 times 2 to the t divided by 3. And again, always make sure that your t value and your a value are in the same units. A is in hours, t is in hours, so we're good. Any questions about how I got that model this time? right, now the question is, how many bacteria are in the colony after 15 hours? So how are we going to find that? Good, right? That's a T value now. So we're just going to plug that into our model to figure out how many bacteria we would have. So we're looking for N of 15. So we've got 1,000 times 2 to the 15 over 3. Now, you could just put all that in the calculator, right? Just make sure your 15 divided by 3 is all grouped together in the exponent. If you do that, okay, I'm going to go ahead and just simplify this one because I can actually do this whole thing by hand. We're going to have 1,000 times 2 to the 15 divided by 3 is 5. Then our next step, order of operations wise, would be to do exponents. What is 2 to the 5th power? Good, 32. So we're going to have 1,000 times 32. And so 1,000 times 32 would give us what? Good, 32,000. And then with these word problems, always think about your units, right? So that's 32,000 what? What did we find? Bacteria, good. So we started with 1,000 bacteria. So after 15 hours, if they're doubling every 3 hours, we would end up with 32,000 bacteria. Any questions on that one? All right, now, next question. After how many hours will the bacteria count reach 100,000? How are we going to do that? Good, right? We're going to set our model equal to 100,000, and we're going to try to figure out what the time would be, right? So we're going to say 100,000 equals 1,000 times 2 to the t divided by 3. All right, so what would our first step be if we're trying to solve for t this time? Good, divide by that 1,000. We need to get the base by itself. 100,000 divided by 1,000, that should give us 100 equals 2 to the t over 3. Then we can do what? Good. Take a log on both sides, right? And again, it doesn't matter if it's a natural log, a common log, either one's fine. I'll use a natural log here. Now, once we've done our log on both sides, then we can do what? Okay, good. Move our exponent out front. So we're going to get natural log of 100 equals t over 3 times the natural log of 2. So then what can we do from there if we're trying to get t by itself? Okay, multiply by the 3. So now we've got 3 natural log of 100 equals t natural log 2. And then our last step. Good, just divide by the natural log of 2. And so now we have t equals, and at that point, right, because we're looking for an amount of time, you would probably want an approximation rather than just 3 natural log of 100 over natural log of 2. So put that in the calculator, and we'll just round that to 2 decimal places. Good. 19.93. And what are those units going to be on our t value this time? Hours. Good. Okay, so almost 20 hours, okay, for our bacteria population to reach 100,000. Okay, so that's where we're going to stop for today. I'll hang out for a couple more minutes in case you got any questions about that one. Again, the homework is not due until Friday at midnight. The test will also be due Friday at midnight. That'll open up on Wednesday night at midnight. So just make sure you're prepared for that. Let me know if you've got any questions about anything. Otherwise, have a great afternoon, and I will see you all on Wednesday.